Okay, so today we're going to be talking about constrained shortest path first, and this is where it gets interesting, because this is where we actually get to do some traffic engineering. I remember last week we pretty much spent the whole day just going through the labs, and if you may recall what we did. What we've done so far, just a bit of a recap with our labs, what we've done is we have first of all configured our interfaces on our MX devices. We've got MX1, MX2, we've configured our interfaces. We have set up our IGP, which in our case is OSPF. We have set up BGP to route between our MX devices. We have set up a routing instance, and those routing instances are acting as customer edge routers. So within the, you may remember that the whole concept of MPLS is that we have got a service provider network, and the traffic is transiting through our network. So it's either transiting through because it's coming from maybe a downstream customer, which may be a downstream ISP, maybe we're a tier 2, maybe we're a downstream tier 3, we're connecting to an upstream tier 1, so maybe the traffic is transiting through from our tier 2 up to our tier 1, and of course traffic coming back the other way. So maybe our goal is to control flow of that traffic. Maybe we're a tier 1, and maybe we are part of the internet backbone, and therefore we are controlling how traffic transits from us through other tier 1s, from us down to our tier 2s, and so on. So we're really, what we're doing with MPLS is we are in a internet service provider, and we're controlling the path. What we aim to do, we aim to control the path that traffic takes as it transits through our autonomous system. Okay, so we're coming into our autonomous system, obviously from another autonomous system. It's coming into our autonomous system, it's going through, and then out into another autonomous system. So that is one scenario where we may use MPLS. The other scenario is where we are actually providing a VPN service to our customers. And we haven't really got into that part yet, but we will. We'll get into how we set up a VPN between customers. So as a service provider, what we're doing is we're saying to our customers, we can offer a VPN service to you. We'll create the VPN, and we will manage the connectivity between all of your sites for you. And that is a very appealing solution to a lot of organizations, because of course organizations are not in the business of networking. That's not their business. Their business is maybe selling a product, maybe providing a service. So it is a fairly appealing proposition to be able to outsource all of that to an ISP whose business it is to do routing. And that is the business of an ISP, connectivity, networking, routing. So there's a fairly appealing proposition to an organisation to just hand it over to an expert, just outsource that. And one example I have talked about before is our local council right here, the Gold Coast City Council, have gone to a local ISP, which is just down the road from our campus here, and they said, hey guys, we want to have connectivity between all of our sites. We don't want to manage that ourselves. We don't want to have to make that happen ourselves. We want you to make it happen. And they'll put in place a service level agreement which dictates and describes and facilitates that whole operation, and then the ISP just goes and takes care of it. Now, that ISP is using MPLS to facilitate that particular VPN situation for our local council. So it's a very appealing proposition for someone to just outsource that. We'll pay you to do it, and you take care of it. So we'll get to that. We haven't got there yet. We will get to that. So what we've done so far is we've looked at setting up a routing instance to act as the customer edge router with a different autonomous system. So our customer edge routers are in a different autonomous system to our PE. PE being our provider edge routers. So within your MX device that you are configuring, your MX device has a routing instance. And so within your MX device, what you are doing is you are controlling the PE function and the CE function within the same device by creating this routing instance. And then what we've done is we have then created a BGP external peering arrangement between our PE and our CE. Okay, so our total BGP situation is we've got this external peer between the PE and the CE. We've got an internal BGP peer between our MX devices, so MX1 and MX2. They've got an iBGP peer because they are indeed the same autonomous system. Okay, so we've got the BGP routes being advertised from our CE to our PE, and then from one PE to another PE, and then from that PE down to the other CE. So we've got across our entire topology, which encompasses actually 3 different autonomous systems, we've got BGP routing across all of it. And then what we've done is we have then taken the local loopback address of our CEs and we have exported that into the BGP routing protocol so that the BGP will then advertise the loopback address for our CEs. Okay, so we've got this reachability. We've got this BGP reachability to the loopback interfaces of our CE. So from one CE we have reachability to the other, which means we now can ping the loopback address of one CE from the other. So that's the BGP. We haven't got into MPLS yet, right? So why are we spending so much time on BGP? Well, because MPLS is dealing with transit traffic that's going between autonomous systems, and the protocol that handles that routing is BGP. So ultimately we have to deal with BGP because it's going to be BGP's job to put the traffic into the ladder switch path. So BGP will choose the LSP that we create as the next hop. So the setup of BGP is critical to the operation of our MPLS ladder switch paths. Okay, so just a bit of a recap. Then what we did is we then created a static ladder switch path where we configured the ingress, the egress. We configured the label value as well. We configured the next hop, or the next router in the path. Now, the network that you are provided with has got a provider core network already built. So all the other labels in the static path were already configured for you inside the provider core. So that was already there. Okay, so all we had to do was configure the first label. And then our static LSP came up. So that was a static LSP. So with the static is you say the ingress router, you specify the egress router, you specify the label value, and you specify the next hop. So all of that is manually created. And then, of course, in a provider network, you would have to go and specify the label values of every router along the entire path. The incoming label values and the outgoing label values for the swaps. Okay. So you have to do all of that work. Then we said, well, wouldn't it be great if we could automate that process and have a way that could just be done automatically, and that's where we introduced these things called label distribution protocols, right, which are also known as signaling protocols because they signal the path for us. And once we created that, then we could simply say, go to the ingress router and say, I want to create a ladder switch path to this egress router. and let the signaling protocol build it for us. And it just built it for us. So the signaling protocol went ahead, figured out what is the path, figured out a path to the egress router through our topology, assigned the label values for us, and built it. And there it was. And then the LSP came up for us, all signaled up by the label distribution protocols. And when we introduced these label distribution protocols, there were two of them. Who can recall what the names of the two label distribution protocols are? Anybody?
LDP?
Yes, LDP was one of them.
Which RSVP?
RSVP is the other one. Exactly, thank you. So we've got RSVP and LDP. LDP actually stands for Label Distribution Protocol. LDP was created before MPLS. RSVP existed prior to MPLS becoming a standard or a technology that was used. But it was extended to provide these label distribution services to MPLS. Previously, RSVP was used to reserve resources on servers. It already was a resource reservation protocol. That was extended now to reserve resources on routers, so that it could facilitate the creation of label switch paths. Now, out of these two protocols, one of them allows us to do network engineering and one of us doesn't. And by network engineering, I mean one of us allows us to specify the path that the label switch path will take. So by the path, I mean the routers that it will use, the routers that it will go through on its way from the ingress router to the egress router. One of those protocols allows us to say, well, you're going to go this router, then that router, then that router, then that router. And the other one simply follows the IGP's best path calculation. Who can remember which one allows us to do traffic engineering out of those two?
RSVP?
It's RSVP. Yes, so it's RSVP that gives us the option to actually control the path that traffic takes. That's quite a desirable feature of RSVP, because one of the issues that we have when we just rely on our IGP is the IGP will always choose the path with the best metrics to get from one point to another. And so what we have, if we have a provider's network with many possible paths through the network from one point to another, the IGP will always choose the best path. So what you end up with is a situation where only one path is ever used, because that's the best path. So all the traffic takes one particular path. So you can end up with certain links or certain routers, certain links on the network being highly utilized because they are the best path, and other parts of the network being not utilized at all because traffic never goes that way. Which is a problem. If you're in the business of selling bandwidth and you've got bandwidth sitting there that is never used because your IGP never uses it, you can never utilize those parts of your network. So that's not really an optimal situation if you're an internet service provider. So what traffic engineering allows us to do, it allows us to specify the path through which traffic will pass. So we get to say, well, if it's going from this point to that point, then I want you to go this way through my network. So you get to tell it the routers that it needs to go through. So that's one of the benefits of traffic engineering, is you get to utilize all the capacity in the network. All right, so what we did last week is we used label distribution protocols to build labels of paths. So we use RSVP and we use LVP. And we just had a look at what they did. Now, with RSVP, what we first of all did is we created a RSVP labels of path, and we just let it go ahead and build the path for us. And what it did is it went to the IGP and it said, okay, well, let me use the IGP to figure out the path from the egress to the egress. And then build a label switch path that simply followed the IGP's best path selection. So that's what it does. If you just kind of leave it to its own devices, that's what RSVP will do. However, if we want to then take control of the path, what we did was we then added a thing called an explicit route object to our RSVP signal path. And our explicit route object then has instructions as to which routers that LSP should traverse. So we then control the path that it took. And we said in our explicit route object, we want you to go here, and we want you to go there, on your way to the egress router. So we control the path that our label switch path took. We applied the explicit route object to our RSVP signal path, and we discovered that the path then changed. So initially the path went one way, and then after we applied our explicit route object to our RSVP path, it went the way that we told it to go. Okay, so we're going to do a little recap on that, and we'll just sort of look at that before we get into our next lab. So we just wanted to sort of highlight that point. So we have this thing called, we discovered last week, that we have this thing called an explicit route object, which allows us to control the path which our traffic takes. Now, what we want to do is we want to get into this constrain shortest path first algorithm, because here's the thing. Last week, we manually set to our explicit route object, go here, then go there, then go there. Okay. Would it be good if we didn't have to figure all that out for ourselves, but we could say things like, well, I want a certain amount of bandwidth on my path, and there are certain, I have a preference for certain types of links over other types of links in my network. I'm just going to tell you what my preferences are, and RSVP, you just go and figure that out for yourself, and you discover what is the best path to my network for me. You figure it out. Wouldn't it be good if we could do that? Well, that's exactly what constraint shortest path first does for us. Instead of us saying, well, go to this router and go to that router, what we're saying is, well, this is what I need, go and build it. And it'll go and figure out for us what is our explicit route object. In fact, it will build our explicit route object. It will then say to RSVP, there's the explicit route object that I've built for you, go and build the path. Okay, which is exactly what this algorithm does. So it's a really nice algorithm, and it is when we're building label switch path, this is the way that is usually done. We use this algorithm to build them for us. So let's go and take a look at what it is, how it works, etc. So we're going to describe the path selection process of RSVP signal label switch paths. First of all, without the use of CSPF. We're going to look at what happens just with it left to its own devices. We're going to describe the IGP extensions needed to build and maintain a TED, or a TED is a traffic engineering database. Okay, it's a database that the CSPF algorithm uses to figure out, to figure out what is our explicit route object, or to build our explicit route object. We're going to look at how the CSPF algorithm selects the best path based on provided constraints, and how administrative groups can be used to influence path selection. Okay, so let's get into the behavior first without CSPF. Now, we actually built this last week, did a lab on this. So the primary benefit of enabling traffic engineering extensions to the OSPF or ISIS is to allow each ingress router to calculate and signal protection paths around a failed link or node. So let's just unpack this statement for a minute. First of all, we have mentioned two IGPs here, OSPF and ISIS. Now, just looking at those two IGPs, what is the common factor with those two IGPs? There's something common, some common factor that relates to those two IGPs. What is it? What do you think of what it might be? They are both link state protocols. Okay, they're both link state protocols. What does that mean? Well, that means that these two IGPs, they don't advertise their routes. In other words, they don't go into their routing tables and advertise their routes in their routing tables to all the other routers. No, they don't. What they do is that they advertise the state of their links. So they will say, I've got this interface connected to this network, and this link is up. I've got this other interface connected to this other network, and that interface is up. And they provide information about their links, including the state of their links, the bandwidth of their links, and so on. So all of this, these what are called link state advertisements, are advertised to other routers. And the routers receive the link state advertisements from all the other routers that they're communicating with, and then they calculate the best path. So the routing table, information in their routing table of a link state router, that information is not received from another router. That information is calculated by the algorithm, the shortest path first algorithm in the route. So the router uses the algorithm to calculate the routes, and then it puts its calculated routes into its routing table. That's unlike other protocols like distance vector protocols, or even BGP, which is a path vector protocol. So BGP doesn't calculate the route. What BGP does is it receives routes from other routers. In fact, it receives lots of routes from other routers, and it just figures out what is the best route to my destination. So I've got all these different possible routes that I've been informed of. Let's take a look at all of them and let's figure out what is the best route to the destination. And it puts its best route into its routing table. So it doesn't really calculate a best path, it just selects a best path out of lots of possible options. Whereas a link state router doesn't receive routes, well, not by default it doesn't, we can make it do that, but by default it doesn't. It will calculate the route. So a link state protocol then has within its own databases a complete picture of the entire topology, whereas other routers do not. Like a BGP router does not have within its database an entire picture of the entire internet. That would be almost impossible. It might just give you the size of it. But it doesn't need to, because that's not the way it works. Whereas an OSPF router and an ISIS router does have within its own databases a picture or a detailed description of the entire topology. Okay? Or at least of its area, or its, in ISIS cases, this is called a level. So an ISIS level is equivalent to an OSPF area. It has a picture of its entire area, and it builds the best routes to that. Okay. So, basically, what we've done with these two protocols is they've been extended. They've been extended to provide additional information. So they already provide their link states, already provide all of that. But now, for the purpose of traffic engineering, we need to know some additional information that we didn't previously know from the standard link state advertisements. So they've been extended to provide extra information so that we can create this thing called a TED, a traffic engineering database with that additional information. We'll get into what that is. But it allows us to do a couple of things. It allows us to calculate a path based on constraints, which is really, really great. But even better than that, it allows us to calculate an alternative path in case our first path fails. So if we've said, okay, I want a path from this ingress to that egress, I need a certain amount of bandwidth. I want you to build a path for me. It says, okay, I'll build a path, there's your path. What happens if that link fails? So what CFDF does is it allows us to then say, that path is no longer available. Let me find another path that meets your requirements. So it meets your bandwidth requirements. And I'll build you another path that has the bandwidth that you need. Okay, so that's one of the greatest, one of the big advantages of CSPF. So we can have these algorithms that we use. One of them is called fast reroute, one of them is called link detection, and it allows us to very quickly establish an alternative path from our ingress to our egress in the case of a link failure. Okay, so first of all, link state protocol. So what you will find then looking at that, is that within an internet service provider, your internal gateway protocol will always be either OSPF or ISIS. You will not find any other IGP running in an internet service provider. Why is that? Well, because we need the extended capability of these link state algorithms to build our traffic engineering database so that we can provide MPLS services, and no other IGP does it. Okay? It has to be link state. Okay, so that's kind of some of the sort of things that we can take out of this statement. All right, so let's get into this and help you understanding of how the LSP path calculation changes when CFDF is deployed. The next few slides are going to review the path calculation with its use. So what we did last week when we built our RSVP signal path, we actually disabled CFDF. Now, the reason we disabled it is because by default it's enabled. Because by default you want it, because of the benefits of it. So usually you don't build path without it. But just for the purpose of learning what it does and just learning of the functionality of CFDF, we're going to look at what happens without it, and then let's compare that to what happens with it, so we can get an understanding of what it does. So let's take a look at the without situation first. So the path message is sent initially by the ingress router, and it requests the reservation of resources by downstream routers and notify those routers of how and where to build the session. So some path message objects are used to specify what is to be reserved. So there's a couple of things here. We've got a label. So one of the things RSVP does is it figures out the labels. It figures out the first label that's going to be pushed, and then it figures out all the swaps all the way along the path, and then it will figure out the fact that the penultimate router is going to be given a label value of 3, so it will then pop the label, and the path and the traffic will be sent to the egress. So it figures all that out. So this we then have this thing called an explicit route object, which we built last week. So the explicit route object specifies the path the session will take. So this is where we get into the traffic engineering. So we're going to say, go here, then go there, then go there. So when an ERO has not been configured, the path message is sent with no ERO along the IGP's shortest calculated path. So it's just going to take the standard IGP best path with no ERO. Okay. So for a non-empty ERO, so when we actually do give it an ERO, which says go here, then go there, then go there, the administrator of the Ingress LSR label switch router must manually configure the explicit path. And that's exactly what we did last week. Now we created this ERO, we turned off our CFPF algorithm, just like on the slide here, the no CSPF. We put the no CFPF statement in there. Then we went ahead and we manually created an ERO. Okay? And then we put that into our path, and we saw that our path then changed from the IGP's default path to the path we had specified within our ERO. That changed. Okay, so that is without CFPF. That's basically how it works. Okay, so without CFPF, we can still reserve bandwidth. So we can be configured to support a particular bandwidth along the path of the LSP. The object that signals the bandwidth is called a T-spec object. It's just the name of the object. In other words, this is a parameter that gets set along the path where RSVP uses this object to say, I need this much bandwidth on this particular link, or on these particular links. So it's signaled by the sender. Each router along the path determines the supportability of requests. What does that mean? That means that the RSVP says, I need this much bandwidth. And then what has to be figured out is, does the router have that much bandwidth available? And that's kind of the supportability issue. If the local downstream LSR is just label switch router, the local downstream LSR along the path cannot support the required bandwidth, the LSP establishment will fail. So you'll come back with a message which says, look, I can't build that LSP because the bandwidth is not available. Okay, so point here is that even without using constraint shorter path first, we still specify a bandwidth requirement. If we have specified a bandwidth, and if we specify a manual ERO, then if that bandwidth is not available on our path, well, the LSP fails. Okay, that is kind of the downside. So it becomes a very manual operation of, oh, okay, well, that path didn't work, maybe I can show this other path, so then you've got to go and figure out what path then has the bandwidth that I need. Right, now, the benefit of using CSPF is it'll figure that out for you. Okay, it'll go and look in this traffic engineering database and it'll be able to work out what path has the bandwidth that you need. So it's a very sort of manual process without CSPF. Now, just sort of following on from that thought of specifying that we need a certain amount of bandwidth, kind of like just sort of following on from the bandwidth thing, is that once we've got our LSP built with our bandwidth, MPLS doesn't actually police the bandwidth. So yes, we need a certain amount of bandwidth, we've built our LSP, it's got our bandwidth, but what happens if the actual traffic that we're sending exceeds the bandwidth? MPLS doesn't by default police that particular traffic, but we can make it. We can make it do that simply by adding this policing filter in there. And we can go ahead and create this policing. So this is the show protocols MPLS. We can put the auto policing statement in there. Class will drop. In other words, we don't care what class of traffic it is. If it goes over our particular bandwidth, we're going to drop it. Okay? Or you could say class best effort drop. In other words, you know what we talk about when we say class? We're talking about class of service. Okay, so we're talking about prioritization, best effort, explode, forwarding, so on. Okay, so we could say, well, we're just going to drop all the best effort traffic, but we're still going to pass our other traffic, even if it goes over that band. So you have some options to how you do this. Okay, so you can police the traffic, you just have to add it in. It doesn't happen by default, but not hard at all to do. Okay, So RSVP bandwidth, let's take a look at this. The physical speed of the interface becomes the RSVP available bandwidth by default. So here's an example of an interface which is a 1 gig interface. So if we take a look at show RSVP interface, we see that this interface is a 1 gig interface and all the bandwidth is available to be reserved by RSVP. Well, it's possible that you may not wish to do that. It's possible that you may wish to leave some bandwidth for other traffic that's not MPLS traffic for that particular, on that particular route, or that particular interface, because maybe there's other stuff that needs to happen on that interface besides MPLS traffic, and you don't want to just allow RSVP to allocate all the available bandwidth for that switch path. So you can change the default behavior. That's the point of that. You can change it. You're not stuck with that situation. Okay, so let's get into the CSPF algorithm, constraint-based routing. So first of all, it is a modified shortest path first algorithm. We integrate this thing called a TED, which stands for a traffic engineering database. So we're integrating this data that's in our traffic engineering database. We're taking we're using our IGP to provide or to build the TED. So the IGP is actually responsible for creating this traffic engineering database. So the IGP topology information, which is available bandwidth, and this thing called administrative group, which we'll get into, determines the optimal path and set up order according to user-provided constraints. So what do we mean by user-provided constraints? Well, what we mean by that is you can say, I want an LSP from here to there. I want a certain amount of bandwidth. I want it to traverse certain routers on the way, so you can still say go here, go there, so you can still put in some requirements of where you want it to go. We can use this thing called administrative groups, which we'll get to, and explain what that is, and then you can put a priority. So you can have LSPs that have different priorities over other LSPs. So you might have a high priority LSP that you're creating that requires a certain amount of bandwidth, but perhaps on the links that you would like that LSP to traverse, there are other LSPs that are using that bandwidth that maybe they've got a lower priority. So what RSVP can do is it can actually pull down the other LSPs off of those links and build your high priority LSP on that link. And then hopefully it will be able to re-signal the other LSPs on other links. Hopefully. Okay, so what we can do is we can put some constraints in there. We can give it, if you like, our wish list. I want this much bandwidth, I want to go through these routers, and this is the priority that I want to give it. So you basically give it your wish list. You can put a maximum hop count in. I only want to have so many hops in my path, no more than that. So you put in, if you like, your constraints, and then CFPF goes and figures out what is there a path, first of all, that meets your constraints, and then if there is, then it goes and chooses one of those available paths. So first of all, what it does is it prunes anything that doesn't qualify. So anything that doesn't meet your requirements. So if it's got too many hops, if it doesn't meet your bandwidth, if it doesn't go through the particular strict or loose routing that you've put in, if it doesn't meet your priority, if it doesn't meet your administrative group's requirement, anything that doesn't meet that is eliminated from the calculation to begin with. And then it looks at what's next. So from what's next, it will then go ahead and create this explicit route object. So the goal of the CSPF algorithm is to create an explicit route object. That's its goal. It then gives the explicit route object to RSVP, and RSVP then will signal the path. with that ERO. Okay, so the outcome of CSPF is an ERO. That's the outcome. That ERO was then given to RSVP to build the pathway. Okay, so there's only two possibilities. We either get an ERO, or we figure out, hey, looking at all your requirements, that particular path is impossible to build. So I can't build a path that meets all your requirements. That has your bandwidth requirements, that has your hop requirements, that has your strict or loose routing requirements. I can't build that path. It's impossible to build that path through the existing topology. Okay. So two possibilities. You either will be able to build a path and therefore come up with an ERO, or won't be able to build a path because what you've asked it to do is impossible to do. Which then you have to go back and, I suppose, change your requirements, won't you? If you really want that path, you'll have to change what you've asked it to build so it will be able to go ahead and build a path. Okay, so far so good. All right, so basically the job of the CSPF algorithm is to evaluate all of your requirements, evaluate the topology, and then figure out, is it possible to build a path that meets your requirements? If it is, it will come up with an ERO. If it isn't, it will come up with an error message saying, nope, we can't build that. Okay. So this, the information is configured on our ingress router. So when we're going to build this path, all of the constraints, the ingress, the egress router information, the requirements of your constraints are all configured on the ingress router. It's the ingress router's job to then figure out if a path can be built. So this function happens on the ingress router. Okay, so we've got our link state database. We have our extended link state information, which is then used to build this traffic engineering database. We then have our constraint shortest path first algorithm, which evaluates your user constraints, which you've given it. So this is your wish list, if you like, of what you want that path to be, what you want it to look like, the bandwidth, the path it has to take, etc. How many hops maybe. I mean, you don't have to put all those things in, you just have to put in the things that you want. You might say, well, all I care about is the bandwidth. That's all I care about. Just put that in. So you put in your user constraints, and it will then evaluate your constraints, consult the traffic engineering database, and come up with an ERO. It will give the ERO to RSVP, and RSVP will then go ahead and build a path for you. Okay. So step one is information is stored from the IGP flooding. So it's the IGP link state information that is stored. The stored traffic engineering, the information is stored in this traffic engineering database, or TED. The constraints are examined. It then calculates a physical path for the LSP. It then builds an explicit route object. It then gives the explicit route object to RSVP. So they are the 6 steps, basically, that CSPF uses. Okay, so let's take a bit of a look at this. How does it get this done? The IGP extensions propagate additional information. Now in ISIS, the extensions are called TLB tuples, and at OSPF they're called opaque LSAs type 10. Don't get too bogged down in the names. Basically, they contain information that is ultimately going to be used to build our traffic engineering database. This information is propagated within an area or level. So OSPF uses areas, ISIS uses levels. So the same concept. so level is already the same concept as an area. So an area, an ISIS level is the same concept as an OSPF area. Okay, so what information are we actually distributing? We're distributing the bandwidth available, administrative groups, the link colors, and the router ID. Okay, so administrative groups. What is this concept of administrative groups? Essentially, what you get to do is you get to look at your overall topology and you get to put different links into these things called administrative groups. The naming convention is to give each administrative group a color name. Now, you could have called it anything, but the common practice is to give it a color name. And so you might have, these are my gold links, these are my bronze links, these are my blue links, these are my red links. And what it does, it allows you as a network administrator to identify links that have some commonality amongst them. Maybe these are my 10 gigabit Ethernet links. Maybe they're my gold links. Maybe my 1 gigabit Ethernet links, or they're my silver links. Okay. Then let's take a look at links that may traverse a certain, may go through a certain number, certain routers. So we've got a topology that spans the whole of the east coast of Australia, and we'll identify those links. Maybe they're my blue links. If we've got other links that maybe go down the west coast, maybe they're my red links. So it's just a way of identifying links and paths within your topology. Maybe there's links that have a certain maybe reliability factor to them. Maybe those links have an uptime of 99%, whereas maybe other links have an uptime of only 90%. So maybe you'd say, well, these links will give those a particular color because of the reliability factor that we're getting with them. And then what you get to do with your constraint shortest path first is you get to say, well, I want this path to take my red links, or I want it to take my blue links, or I want it not to take my red links, or not to take my blue links, or it has to take all my silver links, or none of my silver links. So you get to say these kind of constraints when you're building your latest switch path. So it's just a way of directing traffic by that. So you can have links, this is a silver link, but it also goes down the east coast of Australia, therefore it's a blue link as well. So it's a silver link and a blue link. So you can do all these types of combinations of links. So it's a mechanism that allows an administrator to classify links that have some commonality about them. I mean, you could call it my East Coast links. I mean, you could call it that as well. You don't have to give it a colour. You can call it my West Coast links. You can give it a name. You don't have to give it a colour. But colours are commonly used to classify these links. Okay, and there's the router ID, is also propagated. So here's an example of something, opaque area information that is propagated. So this is OSPF, area 0, opaque area TE LSA, traffic engineering LSA. We've got a length, we've got a link type, we've got a link ID. We have got a bandwidth here. This is in this case, it's a 1 gig link. Maximum reservable bandwidth, we've got all of it is available. And we also can allocate bandwidth to a particular port of origin of LSP. So you can say, well, I've got 7 possible LSP priorities. If I'm setting up an LSP with priority 0, I'm going to allow a certain amount of bandwidth for those LSPs. The LSPs with a different priority, I'm going to allow a different amount of bandwidth for those LSPs. So you can get right into controlling how much bandwidth is available for different priorities of LSPs as well. Okay, so what happens here is that these opaque LSPs are flooded throughout our topology, and they maintain what is called our traffic engineering database. Okay? So the issue here is that whenever a change occurs, so whenever bandwidth is allocated to a later switch path, the information in our head becomes out of date because now the available bandwidth is less than what it was before. So to keep it totally up to date all the time, what we would have to do is we'd have to reflood these LSPs, these state advertisements. We have to reflood these state advertisements to update our traffic engineering database. So if we are building LSPs and tearing down LSPs and moving them around, and all this is happening, then the downside is that we're constantly flooding our topology with these updates, and we're basically swamping our topology with all of these updates. So one of the ways around it is to say, well, we're only going to flood these updates when we have a change of 10%. So if our bandwidth changed by 10%, then we'll do an update. So if we just change it by 5% change, we're not really worried. If we get a 10% change in our available bandwidth, we'll then need to update that information, and then we'll flood these LSAs. So in other words, we don't flood it every single time something changes. We'll flood it when the change is equal to 10%. Okay? So it just limits the amount of updates that get thrown around our network. So there's this update threshold. Now it's configurable. The default is 10%, but you can change it. You can say, well, actually, I'll make it 20%. Or you can say, actually, I want to be more updated, I'll make it 5%. Okay. So you can change it. But that's the default is 10%. It's the update threshold. Okay, so here's our traffic engineering database, used exclusively for calculating the explicit LSP paths across the physical topology, maintains traffic engineering information learned from the IGP extensions. What's in it? It has the up-to-date network topology information, current unreserved bandwidth of links. It contains our administrative groups, which are usually expressed as colors, but it can be expressed as any meaningful classification that means something to you, or that means something to the technical administration team of that ISP. And link priorities, link priority information. Okay, so that is what's contained within our traffic engineering database. Let's have a look at it. Show TED database extensive, but we can take a look at what's in it. This is an ISIS IGP, this particular one we're looking at. So we've got protocol OSPF running as well down here. Okay. So under this, on the OSPF protocol, we've got information about the link, so where this link goes. Logical interface, we've got a color down here. This one's gold. Metric 1 bandwidth. We've got 1,000 megs reservable. We've got 1,000 megs, and we've got all the priorities that we have down there as well. Maximum LSP bandwidth. and so we can set that as well. Okay, so there's the information that's in our TED about in relation to this particular node, this node here, which is the 192.168.2.1 node. Okay, so we can take a look at that once we build our labs. We'll have a TED up and running, and then we'll go and take a look at it, see what's in there. Okay, so after you finish this presentation, what we are going to do, in fact, is going to go straight away into the labs, and we'll actually do this lab. Okay, so I'll do it, take a look at it, and get an understanding of what's happening with the book. Okay, so there's our user provided constraints. So we're going to say bandwidth. We don't have to say any of these things, but we can say any of these things or all of these things if we wish. We can require a bandwidth. We can require a hop count limitation. Administrative groups, priority, set up and hold priority, and we could say an explicit route object. So all of these things are possible. So the process is, so first of all, when the LSPs are requested, it will do this process from the highest priority to the lowest priority LSPs. It will prune the links that don't have enough bandwidth, prune the links that do not contain an included color, or what we should say administrative group, but it doesn't have to be a color, usually it is. Calculate the shortest path from the ingress to the egress consistent with the ERO. If equal cost path exists, in other words, hey, I've got more than one path that I can create, and the equal cost path. So what that means is that the metrics are the same between these paths. If they exist, it will choose the path with the last hop address that equals the LSP's destination. We'll then select, now if we've still got more than one path after that, it will select among the equal cost paths, least hop, then fill related criteria. So we'll get into the fill related criteria, which is used as a tie-breaking mechanism. So once it finally comes up with one path, it will then pass this explicit route object over to RSVP, and RSVP will then use that to go ahead and signal the path. Okay, so that is kind of the process of CSPF. Okay, so just getting back to that issue of setting up a threshold for the flooding of these LSAs to keep our TED up to date, our traffic engineering database up to date. One of the downsides, so there's this balance, right? There's this balance between having our traffic engineering database totally up to date and having our network not swamped by all these LSAs. So there's this balance, is that we want it to be up to date, but we don't want to be swamped by these LSAs. So we have this default which says, well, we're not going to update it until it's changed by 10%. Okay, so the downside of that is that there's a possibility that we might ask for an LSP to be built. CSPF may go into the TED database and say, oh yes, I can build it. It will give the ERO to RSVP. When RSVP tries to build it, it will actually discover that the bandwidth is not available because our TED database was actually a little out of date. And so what happens then is RSVP comes back with a path error message saying, no, I can't build it. And then CSPF goes, oh, okay, I've got to try and find a path. And it could go back into the TED, find the same information, and potentially give the same ERO back to RSVP, which will come back with the same error. So to avoid this kind of hashing of inaccurate EROs because of the delay in our updates, what we do is we then configure this default path retention error. So in other words, if we do get this error, which says, hey, I can't build the path, what happens is we hold this error information for a set time. The default is 20 seconds. You can configure it from 0 to 240 seconds. But what it does is that it absolutely cans the metric on that path. So it absolutely gives it a horrible metric so that it will never ever be selected as a path. And it will hold that for 20 seconds by default, or for more or less depending on what you configure it to be. The default is 20 seconds. It will basically apply an absolutely dreadful metric onto that path so it can never ever be selected again for 20 seconds. Okay? What we're saying is that by 20 seconds our TED database should have been updated and the problem will no longer exist. So it's just this little issue here, this error retention thing, is just to overcome the issue that we had with our TED database possibly being a little out of date, behind what's actually happening on our topology, because we're not flooding every single time we have a change. Okay, so that's kind of where that fits in. All right, what we're going to do now, we're going to take a break, and then we'll get back into some of the finer points of the CSPF algorithm. So let's take a break.